Attention, please. Let's begin. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, there's a comment that I want to make. As many of you know, our men's basketball team has been doing quite well this year. They're ranked 11th in the nation, which is really new and unusual for the University of Tennessee. And we play arch rival Kentucky tonight here on campus. And our success this year is due to many factors, but one of the main factors is our new basketball coach, Bruce Pearl. And to honor Bruce Pearl tonight, a lot of the fans will be wearing their Bruce Pearl mask. And I wanted to share with you, I will be there, and this is my Bruce Pearl mask, okay? Okay. Enough humor for today, right? Our speaker today is a Dr. Aleksey Urmanov. He is a research scientist in the San Diego Physical Sciences Laboratory of Sun Microsystems. Dr. Urmanov is one of our own graduates, as you'll see in just a moment. But he came to us from Russia. He received a BS in mathematics from the Institute of Nuclear Power Engineering in Obninsk, Russia in 1994. I have visited this institute. It's a very beautiful place, and they have lots of good students, and we've had several, and Aleksey is one of them. He also received a master's, an MS degree in system science from the same institute in 1996. At that time, he joined he got one more degree right here, the main one.
Right.
The one from the University of Tennessee is a PhD in nuclear engineering, which he got in 2002. At that point, he joined Sun Microsystems, and he's been there ever since. The title of his presentation today is Reliability Through Telemetry, Advanced Pattern Recognition for High Availability of Complex Engineering Systems. Ladies and gentlemen, please welcome one of our own graduates, Dr. Aleksey Urmanov.
Thank you, Lee, for introduction. Sleeping? Yeah. Hello, everybody. I'm going to talk today about electronic prognostics. This is another title of the same talk. Electronic prognostic is an attempt to figure out or predict when electronic components will fail. And how is it related to nuclear engineering? Turns out that prognostics as a field was started by nuclear engineers, and I'll explain in a minute why. Currently, there is about 66 commercial nuclear power plants in the US, and I think the number 100 is the number of units of reactors. So currently there are about 103 nuclear reactors in this country, and they built a long time ago, and the typical service life of a nuclear power plant is about like 30 to 40 years. So people figure out they spend a lot of money building these nuclear power plants, and then they serve only for 30 years. Something's wrong. So they started to look into the ways to extend the useful life of nuclear power plants. That's where prognostics was born. They tried to prognose, or by using other words, to estimate the remaining useful life of individual components, of individual power plants. So nuclear engineers started the field, and there's a very tight connection between electronic prognostics and nuclear engineering. So they put in place one of the programs that were put in place to estimate the remaining useful life or consider the extension of useful life of power plants were termed plant life extension, PLEX. And the main idea was to look into estimation of remaining useful life of plants and components of the plants and use condition-based maintenance to replace failing components, and by this extend the useful life of nuclear power plants. To do that, they need a very reliable ways of estimating remaining useful life of components. So they look at the degradation mechanisms for different components and how you can get some leading indicators of developing failures and use that to estimate how much longer your plant will be running without any failures. Besides, you have to tie everything to meet the safety critical standards for the nuclear power plant that you can achieve. So, of course, they do remaining useful life estimation during design phase as well. That's what determines the useful life, the design useful life, but that's done for a population of nuclear power plants, not for individual plants. It doesn't take into account the individual specifics of individual power plant, environment, load profiles, or current conditions of the nuclear power plant. So when they do remaining useful life estimation for individual plants during its operation, that's prognostics. And this is a very rich field and very developing right now, and there are a lot of great results were made in the nuclear engineering field. Right now, we're looking into adopting or transferring this technology into computer world. So electronic prognostics in computers, I'll give you a little glance of some microsystems and why we got interested in prognostics technologies in estimating remaining useful life and seeing when things will fail. Sun is making computer servers. We call them servers. Those computers from little boxes seen on the right, like they have only one CPU and very similar to PCs, the ones you use at your home. But then we also have on the other end the high-level computer systems. Those have hundreds of CPUs and terabytes of memory, and they're dedicated to run business-critical applications like most of the banks and financial organizations or big simulation companies. They have data centers filled with the hundreds of those high-end computers. So in the specifics of running a business-critical or mission-critical application is that you have to provide very high availability for your system. It always should be online, it always should crunch numbers, it always should process some database transactions, so it always should be available. So when you go to Amazon.com to look for a book or to buy a book, it always should be reachable like in a second. Once you type the name Amazon.com, it disappears. And even more critical, when you decide to pay, you can't get a hourglass when you decide to pay. It should be instant, it should work. Otherwise, you just move to a different site and they lose you as a customer. So the main requirements to those systems is very, very high availability. And of course, it's very related to high reliability. So Sun also makes software from operating systems. Solaris is our operating system. It's a Unix flavor, by far the most successful Unix flavor. We do Java, and we do storage workstations, which is kind of similar to PCs, but high-end PCs, I would say, and thin clients and small things. And Sun also does very cool stuff. That's on the right. It's a new server Sun is coming up. It has only one CPU. It's physically one CPU, but it has 4 cores, and each core can run 4 threads. What it means basically instead of one CPU, you have 32 CPUs. So this little box on the right have almost the processing power of the very high-end server, and it consumes the power of a light bulb. So the high-end server uses up to 20 kilowatts of energy. That's a lot of power, considering if you have hundreds of those servers in your data center. But this new technology, very low energy and very high performance rate. So this is the cool part about Sun. We're always on the edge of technology and come up with new products to blow away competition. So specifics, there are some specifics about computer systems. When I try to consider computer systems, most of the elements, they have some kind of random nature. They happen, you cannot predict them. Like the user gets on and starts some application. There's a wide range of environmental conditions or variables that can affect your system. Humidity, temperature. If you have high humidity, you have corrosion and all those bad things. If you have low humidity, you get static, and both of these are bad for electronics and computers. So, and there is also no unified framework to analyze reliability or remaining useful life of various components. Each individual component has its own specific. So, what's good about this? These are the characteristics of pretty much any complex engineering systems. So, there is not too much new to the computers. Let's look at some definitions. So, prognostics, it's just a part of the reliability theory that addresses the estimation of remaining useful life of components or systems. And during design phase, you get mean time between failures, so remaining useful life or service life of your system as estimated for population, not for the system you just bought, it's just in general. But each customer actually is interested in its own system. I don't care that in general they last 10 years. I care about mine because in general they can last 10 years, but mine will fail like in next year. I don't like it. So they're really interested in individual prognosis. In the numbers, when I say, hey, your specific particular system you just bought will last 10 years and then it's going to fail, we'll give you an advanced warning that it's going to fail, so you have to do some maintenance actions on it. So what kind of questions prognostics can answer? Those obviously, is it safe to operate either like a nuclear power plant or a computer data center? Computer data centers can have thermal events. We call them thermal events. That means that it almost catches fire. So it happens. Not with some computers, of course, but with our competitors. So what is the probability of a catastrophic event? Meaning, it's like an electric power grid. You have a big data centers, all these computers connected between each other. Some can serve network purposes, some serve database purposes, but if one of the computers goes down for whatever reason, you don't really want that entire data center goes down. That was a catastrophic failure. And it's possible. There are some machines that provide that type of service that if it goes down, the entire data center goes down. You don't really want that. So prognostics can answer that question too. So it also answers how reliable or available your system for the current condition of your system and for the history of usage of your system. Also can answer the question how your particular system compares to all other systems out there. So industry has some experience with prognostics. The richest experience, of course, with nuclear power plants and avionics. They've been using this for quite a while for mechanical and thermomechanical systems. So they use different tricks to evaluate. Of course, for big systems, you have to do inspection. You have to use special instrumentation to assess the degradation or level of damage of different materials. But they also use so-called canners. This is a really neat trick. If you have a system, you can kind of design a system that's similar to your original system, but it's more susceptible to the degradation mechanism. So it will fail sooner, like 2 times sooner than the original system. So when your cannery fails, you know that the original system is going to fail really soon. So this is a really simple and very useful concept. So in electronics, we're interested in electronics. The industry typically looking at such parameters as voltage, currents, temperatures, responses of your electronic circuits, noise on your buses, leakage current, and other operating patterns. So there's a lot of signals you can extract from electronic components, monitor them, and get leading indicators of failures, and schedule a condition-based maintenance, and make sure failures don't happen in your data center. So if you want to design a successful electronic prognostic system, it usually has 3 major elements. You have to have models describing, those can be physical, theoretical, or empirical models describing degradation mechanisms for various components. Of course, you choose the most critical components in the beginning. Then you have to have a systematic way of evaluating the reliability, the remaining useful life of your components and your entire system. And then you have, of course, have algorithms and computing power to do all of this. Prognostic methodology usually divided in 3 clear steps. collect, analyze, and act. During collect phase, you collect all information that is available about your system. That can be just time series of voltage or temperatures, environment variables, or technical information, or specs on your components, or data expert knowledge and opinions on the current condition of your systems. Then you go to analyze phase, where you actually process your data and do the remaining useful life estimation, basically predicting what's the condition of your system and when it's gonna fail. And then act. During this phase, you decide what you're gonna do. Now you know that it's gonna fail in next month with 95% of probability. What are your actions? You wanna go and do maintenance? You're going to just replace the system? Or you may choose to do nothing, just wait until it fails, take your chances. So there's a block diagram just representing the different information you can collect. There's a technical specs, online inspection, online monitoring when you monitor the signals coming out from your system, or just online diagnostics, because most of the computer systems, they have built-in tests, and the results of this built-in diagnostics actually available, and you can use them. Also, then during the analyze phase, you basically bring all these data together, create a database, and then mine those data in the database, and do the remaining useful life estimation on this, and then act. You can choose option 1, which is just aging mitigation. So you can try to do maintenance, you can try to implement improved policies, you can try to see if your degradation process is too fast or too slow, and implement different operating conditions to kind of slow down the degradation process. Option 2, you choose to do nothing, just collect the data, your system knowledge base. Option 3, you can do system renewal. These are inspection, repair, replacement. And another option, you can, if you know that one particular subsystem is actually degrading or has some indicators of degradation, you can pay close attention to a subsystem, because the computer systems, they're so complex, there's so tons of amount of information you can collect. You cannot afford to collect all the information at all the time. The amount of information is vast. That's why you're trying to focus on a specific components, on specific nodes, and if you see there's a suspect node, you pay more attention to that node. You increase your sampling rate, you start collecting more diagnostic information on this node, and so forth. So let's look briefly at how you can estimate the remaining useful life of a system or a component. How do failures occur? What is a failure? So failures are random events. You cannot predict them, but they all caused by some physical mechanisms which develop in time. So if you can get leading indicators of some of the degradation mechanisms, you can actually predict not the exact time, but the interval, and give a probability when a specific failure is going to happen within these time bounds. So to be able to treat this problem mathematically, people had to come up with this model, which is a failure is modeled as the load-bearing capability crossing a critical threshold, meaning the system degrades, and then once it touches some threshold, a failure occurs basically. And graphically it represented as some kind of drifting process that has a tendency to go up and down, and was random in nature. So if it goes up, it's kind of your system degrading, and once it touches some threshold, a failure occurs, the system goes down. So if you can get some kind of statistical characteristics of this degradation process, and you will be able to extrapolate, to extract a trend, and actually compute when it's going to touch the threshold, the critical threshold. And then you give the time, hey, look, in 2 years or in 1 year or next week, your system is going to fail. So there is a simple parametric model when your degradation process has some regular trend and plus some random component which is unpredictable due to the quality of data you collect, due to the inaccuracy of mathematical model. All the mathematical model are abstraction. They describe physical processes to some degree of accuracy, so there's always uncertainty involved. That's why you don't want to model your degradation process as some kind of regular trend, because you will be making huge errors in your predictions. So that's how the predictions made. When it's the simple case, and randomness in this case is just the speed of your degradation. So each one basically represents an individual system. You have a population, but each system degrades one a little bit slower, one a little bit faster. And when you plot the degradation processes for all the systems, you get that type of picture when you have a lot of curves that go up and then cross the critical threshold at random points. And when you basically collect all these points when individual degradation processes cross the threshold, you can estimate the probability density function that gives you the distribution of your useful life or remaining useful life. When you do that, now you can tell that my specific systems, or on general systems of this type, serve about 10 years plus minus 5 years. And this is kind of design phase where you analyze your components, your subsystems, your systems, and come up with the final number. For a nuclear power plant, that would be the mean life of the 30 years. That's the final number you get from this analysis. So those were parametric methods, meaning you have no idea of how a actual degradation process looks like. So you try to use a parametric model. You guess, let's see, my degradation process is linear, so it increases with time as a linear function of time. But you don't know exactly its parameters. What is the speed of increasing? You observe your system, you collect your data, and trying to estimate the speed or the slope of your linear degradation process, and then use this parametric model with estimated parameters to predict when it's going to cross the threshold. There are different types of models. This is called analytical models. You just have a trend and some random components. This is the most simplest. And you can answer two main questions when I do that type of modeling. What is the current condition of my system, and what condition will be in like 2 weeks? So you do prognosis in future that tells you what the condition of your system will be in 2 weeks. Or you can solve an inverse problem. You say, given that my system fails sometimes in the future, what would be the time when it fails? So it's kind of an inverse problem. You don't care about condition. You just tell that the condition of my system is going to be such that it failed. So give me the time when it's going to happen. Two major problems in prognostics. And you can answer them by using that type of analysis. So this is the same thing, only using probabilistic framework. I just want to skip these slides because they're really technical. If somebody really interested in how it's done from mathematical point of view, you're more than encouraged to just read through this in more details. This is a more advanced model. It's called birth and death processes. So basically at each time step, you say that my degradation goes one step up or one step down. When it's going down, it's improving. And there are such processes that can actually improve with time. When it goes up, it's degrading even more. So when you plot, you get a picture like this. And again, from these parameters, you can estimate the parameters for your model and compute the remaining useful life distribution. And actually, that model was the first where they theoretically show the theoretical distribution for the remaining useful life. Turns out it looks like it's more complicated, but it's easier to treat it mathematically, surprisingly. Some more they use right now diffusion processes to get closer to the physics of failure, different failures. And this is the application part. This is how we implement all this theory for real computer systems. I should mention that the mission of our group within SUN is to transfer technology, find cool theoretic approaches out there in academia and industry and implement them, demonstrate them, that we can solve successfully the problems for our own systems, and transfer the technology so the product teams will implement it and start use it for current products. So this is how our work usually looks. We take a server, big server, small server, we collect sensor signals from this server and put them in storage. We also put environmental data in this storage because environment affects computer systems very strongly. Then we have all kinds of data mining routines that run on this data and trying to find failure indicators for various components or find some relationships between data, generate some useful knowledge. Then we display it or use it for control of fault detection and isolation. So to close the loop, we use this data to do intelligent control. Those servers, they're big, they have a lot of fans to push the air to cool the component, and you have to control those fans because if they just run at a fixed speed, they consume a lot of power. And since that box consumes around 20 kilowatt, you're really interested to save 1-2 kilowatt here and there. It saves a lot of money to our customers, considering they have hundreds of those machines. And the energy bills are enormous right now. This is a telemetry infrastructure as we see it. Each box is a computer system. It has a continuous system telemetry harness framework on it, which abstracts the notion of collecting data, detecting various events, failure events or configuration changes events, and then all this information should work really well with the software that runs on this particular system, with the operating system, with the software on the service processor. All these big servers, they have a smaller computers that actually control the operability of the big machines, and they run some diagnostic on them. So all this should be coordinated, brought together in some consistent systematic manner and sent to database where it's analyzed and some useful knowledge is generated from it. This picture represents the types of data we collect from computer systems. If you look at the big computer system, it has a lot of hardware, a lot of electronics in it, plus it has a lot of software running on it. Various types. It could be database or mail program or different simulation packages. So to analyze those data, to evaluate the condition of your computer system, you have to bring all these various data together. Could be physical variables. Those are parameters like temperature, voltages, currents within your systems, or response times, or some other diagnostics information. On the right is soft variables. Those are variables that represent the health or condition of various software packages that run on the server. Those could be CPU loads, memory utilization, and some other parameters. Plus we have so-called canary variables. And a good example of a canary variable, you just try to log into Amazon.com every 10 minutes and measure the time it takes for you to buy something, and use this as a measurable measure of how available the service. And if it starts to take longer to buy something from Amazon, you don't have to buy, right? You make an attempt to buy, and that's more than enough. You don't have to spend money doing that type of analysis. So if it takes longer to buy something, it means something's going on wrong, and you have to address this issue. Those are a type of canary variables we use. Then we brought all this together in so-called black box recorder, where we collect all this data. And then do your analysis. We use pattern recognition very extensively, because once you brought data, you have to do something with it. And the amount of data is so huge that you cannot rely on a human being just looking at the data and seeing, oh, this signal is going that way and that signal going this way. It means something's failing. Human they can do that, but it doesn't scale. You can have a human operator monitor one system or two systems, but when we're talking about a data center with thousands of servers, you have to automate this process. That's what pattern recognition allows you to do. It allows you to basically capture the expertise of human operators, of human experts in a piece of software, and then run this piece of software on data and find possible problems, faults, and the relationship between data. Then you'll start to see development failures and make preventive actions and avoid failures, avoid expensive downtime of your data centers. This is an example how bad signals could be inside the computer system. They're not clean. If you look at them, they have varying sampling rates because they're not supposed to be. They use systems to sample data that are very cheap, so there's no control, too much control over sampling rates. So the sampling rates vary. There's a huge quantization. These signals are severely quantized. Sometimes you get a signal which is just a flat line for the entire life of your server. So it's fixed at, say, 30 degrees, and that's it. It's not changing. So there's no use of such signal. So data preprocessing is a big issue for successful electronic prognostics. You have to be aware of all imperfection of your data, and when you apply your analysis, you have to include it into consideration, because most of the methods you use to analyze your data, they make assumptions. Sometimes those are reasonable assumptions, sometimes not. And very few methods consider that your data, input data, might have uncertainties. And your data not only have uncertainties, they also can be just horrible like this in terms of quantization effect, and sometimes they can be wrong. You can be reading information from a wrong sensor. That happened. That happened. And you can notice that we have a really nice several examples when a temperature readings will jump up and down by 30 degrees, and the sampling rate was like every second, for example. So every second the temperature 10 degrees Celsius, 40 degrees Celsius, 10 degrees Celsius, 40 degrees Celsius. There is no way a physical component like a power supply that has very much a lot of thermal mass can change temperature that fast. What it was root cause to a failed sensor. And without monitoring this stuff, you wouldn't root cause this. And nobody noticed that. The way how they finally noticed that the fans would go on high and low all the time when the environment wouldn't change, and when the load profile on the server wouldn't change. So you're not supposed that the fans should change speed. So somebody just noticed that, some engineer noticed that. So we take a look, and surely enough, we found problems with the sensors. So sensor validation is huge in nuclear power plants, sensor validation and calibration, because they make critical decisions based on sensor measurements. Same thing with computers. Maybe they're not that critical, but it's very important to assure that you're reading the right measurements and those are correct measurements. So again, this is another technology transfer from nuclear engineering to computer world, sensor operability validation. Nobody else is doing this except some. This is amazing. I went at some conference where Intel and others were presenting their autonomic and advanced intelligence system for monitoring computer systems. So they used sensor measurements, of course, to make their decision. I asked them, how do you know that the sensor measurements are fine? They said they didn't have anything to say. They didn't even think about this. It's because there is no connection between those companies and nuclear engineering, right? This is another problem we were able to root cause. So this is a very nice problem. Processors, they have up to 1,000 pins. You connect it to a printed circuit board, and to connect you use a socket. And it turns out that we noticed that some of the systems were failing at a higher rate, and everybody thought it's either faulty processors or faulty power supplies. And when we collected data, we found out that the voltage supplied to these processors has a slight drift sometimes, but it's supposed to be flat, stable. It's supposed to be well regulated at the processor, and it wasn't. So we take a closer look, and we found out that the problem was root cause actually to the faulty socket, to the attach mechanism. So the pressure wasn't even on the socket, so the contacts of the circuit would change resistance with time. And with modern transfer rate and clock rates, even a slight change in resistance at random time, it can be disastrous. That's why we saw some problems. So, and we root cause this problem only because the fact we monitored the signal collected from these systems. So it was root cause and fix, and it was a big success. Actually, we had to go to the completely different socket type to avoid this problem. This is just a picture how it looks like. This is a CPU. This is a huge heatsink, and it's actually a small heatsink. New generation of CPUs, they use much larger heatsinks. I don't want to touch it several times. Okay, I went far away. And that's the circuit. That was a problematic circuit, but we successfully solved this problem. That was a great success for our technology. And this is how we detected this first time when we not even instrumented, we start to collecting these signals in time. And we see that one of the best voltages on two different CPUs on the same board, because one system board has at least 4 CPUs for high-end servers. So on the left, the voltage is flat, very well regulated as it should be. On the right, this is a faulty socket. The voltage drifts a little bit, and this reflects the change in resistance of the pins of the socket. And then there is a temperature event, just air conditioner kicks on, and there is a slight temperature change, like 5-10 degrees in the room. And you see a reset phenomenon when the voltage kind of drops and then started to raise again. So that was a signature, basically, a signature of something wrong with the socket. And we use these signatures extensively to diagnose faulty sockets. But it's all in past. But it was a great success. It basically gave a huge boost to proactive fault diagnostic technologies. This is just another picture showing how the signature of a faulty component. Another great application we had is a detection of cracked solder joints. There is no electrical way to detect a crack in your solder connection in electronics. And that was a big problem because electronic solder connections tend to crack. When they crack, they can create intermittent open, so basically you have intermittent failures, the electronic fails, and you don't really know what's wrong until you actually open it, examine it, and find cracks, but it's too late. You want to do it proactively and detect them before they cause any problems, before your system goes down because of the cracks. So we looked at a couple of cases where the problems were root cause to cracking inside the, say, power supplies in this case. And we noticed that actually, if you monitor a power supply like this, you can see some indications of cracking in the, say, output voltage, some kind of spikes or something else. And by the way, this is a really fine example. You can see that the printed circuit board not really flat, it's kind of bowed a little, and it happened because when you attach this power supply to board, the heights of plastic columns and these metal things not even. One of those is slightly lower than the other, so you have a mechanical stress, and as time goes on, the pins got just pushed through the printed circuit board, so it cracks. When it cracks, it causes problems. So you would like to detect this, but before they fail permanently, they start to produce various intermittent faults, which is not significant enough to cause a system crash, but you can detect them and avoid system crash down the road. This is a just nice picture of cracking, how bad it can be. And by the way, if you put this power supply in your computer system, it will work fine. That's what makes it difficult. But it will fail eventually. Maybe in a year, maybe tomorrow. That's why we go to the next level when we're trying to predict, assess online the severity of the damage and estimate what is the remaining life of these power supplies if the cracks have that level of degradation. So you can schedule your maintenance event. You don't have to say, oh, I have to shut down everything right away and change this power supply. You can wait until a planned downtime when you plan to upgrade something or do some kind of other maintenance, and then use replace those power supplies. This is just a signature that can be seen in the output voltage that's representative of a crack, which all our technology implemented in software. We don't require any additional instrumentation, any additional sensors or hardware inside our system. That's why it has a great success, because it can be readily available for our current systems. You just install a software package on your system, and now you have all this ability to monitor your system and catch those leading indicators to some problems. Another fine example is how the root cause problems, again, to power supply. It's very interesting. You have a computer server that has very complicated CPUs, memory devices, all these high-tech devices, but the main components that fail inside those high-tech devices are pretty low-tech devices, like power supplies, fans stop rotating and the system overheats and starts failing, or power supplies that quit working, or something else. So most of the components, or most of the return on investment, is in addressing those low-tech devices to improve their availability and reliability. And in past, usually what people did, they use redundancies. So instead of putting one power supply, they put two. But there's exactly the same power supply. They have exactly the same degradation mechanism like this in cracking. So one fails, then the other will fail. So look, you have to go an extra step. You have to analyze, monitor it, as we do with equipment in nuclear power plants. So again, power supplies, they have internal cracks in this case, and after a while it just dies, and when it dies, it crashes the entire system. So, and if you run a business critical application, it's a devastating. You lose millions per hour. That's because our customers has no sense of humor about these things. So you have to make sure your systems are really reliable and free of such faults or faulty components. So our solution was to this: install continuous system telemetry harness, which is just a piece of software that collects the data and uses developed by us detectors, those based on pattern recognition or other statistical analysis, and use those to look for those signatures and indicate, hey, there's something wrong going with your system, you better go and replace this specific component right away before it crashes your system. And customers just love it. Just love it. It's like the answer to most of their problems. So for this particular power supply, we actually had to make a test stand because we got a bunch of power supplies returned from the field, and there were no trouble found, meaning it failed in the field, it got into a repair shop, they tested it, it's working fine, so they had no clue why it failed in the field. So we got a bunch of those power supplies and started testing. We just did accelerating testing with temperature. So that was our setup. This is a part of a high-end server, previous generation of high-end server. What I see, these are the space where we put system boards, about 8 or 9 system boards. Each system board has 4 CPUs and a bunch of DC to DC converters. So this is the DC to DC converter we were interested in because it supplied voltage to the processors. So this voltage should be of very good quality. Something going wrong with this power supply, your processor will have errors in it. What we did, we used our interns for thermal margining of the power supplies. We made a simple thermal jacket and put it on, take it off, put it on, take it off every 2 hours. That's why we need interns to do that kind of work. So eventually, we basically did the accelerated life studies of the power supply by doing this thermal cycling of the power supply, trying to accelerate the degradation mechanism so we can get it to failure. And what we saw for good power supply, you can change the temperature like high, low, high, low, high, low, but the output voltage stays very flat. It's very well regulated. Everything working fine for good power supply. But for faulty power supply, when you do temperature changes, you will see instabilities in the output voltage, which are very infrequent and very rare and intermittent in nature. If you stop thermal cycles, they go away. The signal is flat. That was because of no trouble found. Because you have a faulty power supply. Once in a while, when something happens, like a temperature drop or some other factor, it will produce a spike like this. And this spike actually causes the processor to fail with some kind of error, which is related to internal structure of the processor. So you cannot, if you don't monitor that voltage, you have no way of relating the error that happens inside CPU to the input voltage on this CPU. And that was a big source of no trouble found when you have a failure at customer side and the error reports it's a faulty CPU. So you take the system board, you bring it home, you start testing it. Everything's fine because you didn't do thermal cycling, or you cannot actually reproduce the conditions that were at the customer side. So we didn't notice anything besides, as it was in past, they didn't actually monitor the voltage of power supply in time. So even if they actually had some spikes, they wouldn't notice. So it wasn't, what they call it, like insufficient coverage. You basically didn't see that type of degradation. We were able to demonstrate that this is what's happening inside those systems, and this is what actually causes processor errors. And this was a great success for our technology that demonstrated the value of it. This is another example that demonstrates also the instabilities of the output voltage for a faulty power supply and related to the system events. When a system crashes, basically, we had to pull out these graphs to demonstrate that indeed those times coincide when you have a spike, you have an error on your CPU, because there is no other way you can actually relate. And after you show that, the designers will say, oh, of course, you will have errors on your CPU because your voltage is that bad. But until you present the evidence, it's very hard to push through this technology. No trouble found. It's an abbreviation for no trouble found. In some industry, they call it no error found, or like something failed on retest, meaning they retested and everything was fine. It basically addresses this issue. It fails somewhere, you bring it home, you test it, you don't find anything wrong with that. So you don't really know what is it. And actually, it's a very, very expensive item for companies. When you have a big rate of no trouble found, it hurts your company because there's all warranties equipment. So you have an error, you have to replace the component for free. You bring it home, you don't know what to do with it because it's okay, but you know it failed before, so you can't resell it. And you don't want to throw it away because it's a new component, so you have no idea what to do with it. And the system boards for those servers, they cost $100,000 per each, so it's a lot of money. So it's a nasty problem in the computer industry, and not only in computer industry, in the electronics industry as a whole. And we were able to demonstrate successfully that we significantly reduced, or in most cases just eliminated this problem. This is just another example. It turns out most of our examples with power supplies, it's like the weakest link in any system because the quality is very critical of the voltage. If something goes wrong with the power supply, you don't care about anything else. Another example is when again cracking. There was internal cracking inside the power supply, but in this case the situation was more difficult because we weren't able to access any signals from this power supply except temperatures. We didn't have any voltage sensors or current sensors, so we had to work only with temperatures. And it turns out when we studied this case that by evaluating the efficiency of the power supply, you can actually see the change in efficiency when there are internal cracks. So by monitoring the efficiency of the power supply in time, you can actually see when the failure comes and proactively replace it. Oh, this is some map how you can get efficiency of the power supply from the only temperature measurement. Of course, there is no way you can get absolute values with only temperature measurements. What you have to do, you have to have several of such power supplies and compare the efficiency of one power supply in terms of efficiency of the other power supply. Luckily, in those systems, there's a kind of multiple power supplies. You have several, and it will work very well. And so what we demonstrate is what's shown on these pictures. These are the temperatures of very good power supply in various locations and estimations. So what you end up in estimating the ratio of efficiency of power supply. And when it's on the order like 3-4%, you know something's going wrong with the power supply. And when we showed that, the designers actually did an in-depth study when they put external instrumentation and measured actual efficiency of the power supply. And they confirmed indeed if the power supply had internal cracks in it, the efficiency of it drops 3-4%. So that was a great success also for our technology. And this is a demonstration. So in addition to develop different technologies and implement them, we also make little pieces of software when you actually plot the data, you plot the results, and you demonstrate, you go and different conferences or internal workshops, and you actually demonstrate it on live systems and everything running. So those demonstrating how a failed sensor can ruin the control. And unless you monitor the sensor, unless you check its operability, you don't know if it's failing or not. And since you base critical control decision of it, you have to make sure the sensors are good. Another screen just shows a screen grab of a component. We programmed this one in a lab view for electronic components for detection and isolation. So basically here you collect signals, you build empirical or some mathematical models of these signals when everything's fine in your system, and then you start monitor it in time and compare actual measurements with the outputs of your model. And when the residual is too big, you know there's something wrong, and then you can pinpoint the actual trouble location. This is again inferential sensing. When it cannot access a specific measurement, you can actually devise a mathematical model that's called inferential sensor, when it can use related pieces of information to infer a sensor value. And this concludes my presentation. Thank you. So if you want to learn more about some microsystem, there's an address. If you want to learn more about electronic prognostics and pattern recognition, how we apply it, please send me an email. Also, you can send me interesting papers you find related to this, or interesting result in nuclear engineering, because we're always interested in finding new technology that can be applicable to computers. It's a big field, and we have a lot of need for great technologies that were originated here.
Okay. Well, this presentation is now open for questions and comments. Okay, Belle? Yeah, let's do this. Thanks for reminding me.
Aleksey, you showed several failure density functions.
Yes.
Are they estimated from actual data or from simulation?
They estimated from simulations for this presentation. Those are simulated data.
Solder alloys are not known for being brittle. Are these true internal cracks, or are they interface failures? Perhaps due to lack of...
They're interface failures, and it always happens due to stress which not supposed to be there, as I showed, when something bends and actually put an extra stress on soldered joint. So it's not like everything's fine and you develop cracks. It's not cracking naturally, it's just because there is some tension and something pushing and pulling, and then they develop cracks.
Okay. While you think of another question, I have a question. You mentioned Sun's competitors. Who are some of Sun's competitors, and what are they doing to improve the reliability of their systems?
There is no competition to Sun.
He actually paid me to ask that question.
So IBM makes great systems, but they're way too expensive for customers. And who else? Everything else is the systems are much lower quality than ours. So Sun has the greatest performance to money ratio. Plus, with the implementation and incorporation of this advanced technology, we just on the front. Nobody else has this technology. So it's a real differentiator for our customers. We were able to transfer this technology. The technology itself, patently, is not new. It's been used for years, but not in computer industry. We were able to adapt it, to bring and implement actually, and field it. So it's one on our customer sites. So it's pretty cool.
Okay, Hamp.
Use
this.
Have you considered looking at all the variables and multivariate rather than
some of our models are multivariate.
Multivariate.
Yes, multivariate, because some of the cases you cannot see any indications if you look at in one dimension and one signal. There's an interplay with different factors you have to take into account. Yeah,
so what are you assuming then in the multivariate case? Gaussian?
In most cases, for fast implementations, using Gaussian, of course. It makes the analysis much more easier and fast. And since they didn't use anything before that, any simple implementation, simple technique would work just fine. And if you applied more advanced stuff, and you can save even more and be more effective.
Okay, Dr. Ruggles, you have a question?
I used to work for one of your competitors, and about 20 years ago, IBM would do this sort of thing, but it was on the manufacturing side. Multi-layer printed wire boards, and you made thousands of them.
Mm-hmm.
You can pay attention to the manufacturing facility with intentions of making sure that you don't drift off.
Exactly. Yeah, we also have our part in manufacturing. When actually they ask us to install our technology during manufacturing process. Sun doesn't manufacture, it assembles. So all other companies manufacture for us. We just bring all the components in one location and put them together, test the complete system and ship them out. During testing, we do a lot of this. Just make sure the systems we ship, they're free of any kinds of degradation and faults, and that was very useful.
Okay, let me remind everyone that we do have a reception downstairs with refreshments, food, and everyone is invited. But before we adjourn, let's express our appreciation to Dr. Urmanov for his presentation.
Oh, thank you.
Very good. Thank you. You did well.